Tutorial 8, question 1. So let's read the question. Check that the two-dimensional force F is given by is conservative by partially differentiating the components F in a suitable manner. And then find a potential function for F and calculate the work done by F on a point mass which moves the point from this coordinate to the next coordinate. Okay, so there's a typo here. Apparently this is 2x y minus 1. Yeah. So what's this question about? This question about conservative forces. Conservative forces. Or rather a conservative force field. Okay. So you know force as a vector. Yeah. But a force field is basically a vector function for force. Okay, so at one point you have a force applied. Then you go to another point, there's another force applied, and another point, there's another force applied. Okay, so that's what it means by force field. Okay, at every point on the xy plane, there is a force applied at a particular coordinate. Okay, so what does it mean to describe a force field as conservative? Okay, so here's the definition of a conservative force field. Okay, so so let me write down the definition first. Okay, so when someone says F is conservative, by definition, it means that nabla cross F is equal to the zero vector. Okay, nabla cross F is equal to the zero vector. Okay, and remember, by definition also, the name of nabla cross is curl. So what we're doing is we're finding the curl of F. Yeah. So don't think too much about the word conservative. I know conservative has other meanings in English. Okay. Yeah. The word conservative itself has other meanings of English, but for the discussion of vector calculus, the definition of conservative means that, okay, if a force field is described as conservative, it means that the curl of that field is equal to 0. Okay? So forget about all the other definitions of conservative that you know. For the discussion of vector calculus, conservative just means nabla cross F is equal to the 0 vector. Okay, so what's so important about conservative force fields? The importance of conservative force field is that, okay, here's the point that you need to know. Okay, so this is what I wrote down here. If F is conservative, it has a potential function phi. Okay, so this is the importance of knowing whether a force field is conservative. Okay, and we don't know what this is, right? So let's discuss what is a potential function. Okay, a potential function is a function such that nabla of that function, okay, nabla of the potential function will give you the force field. Okay, so this is what you need to know. Okay, so let's start from the beginning. First, you need to check nabla cross F. Is it equal to the 0 vector? Okay, if it is, then we can call this force as conservative. So what's so special about conservative forces? Okay, the special property about conservative forces is that it has a potential function phi. Okay, potential function phi. And what is the potential function? The potential function is a function such that nabla phi is equal to F. Okay, so this one is called the gradient operator. Okay, so remember, nabla taken on a scalar function is called the gradient operator. Okay, so what I'm doing here is gradient of phi. Okay, so that's the left-hand side of this equation. Okay. And so what is the value behind knowing the potential function? The value of the potential function is this. It allows us to quickly calculate the work done by a conservative force. Okay, to quickly calculate the work done by a conservative force. Okay, so phi2 is the value of phi at the endpoint. Okay, so value of phi at the endpoint, and then phi1 is the value of phi at the starting point. So what do I mean? Okay, suppose you have a point mass. Okay, just some mass, and what you do is you are pushing it through through the xy plane with some force. Okay, with some force field. So you push it through like that. Okay, so it starts out here and then it ends here. Okay, because you are applying a force and then you displace the mass, you have done work, right? Because work is force multiplied by displacement. So remember in the last class, we can calculate this work using line integrals. Okay, line integrals f dot dr. Problem is, you notice that line integrals are a bit complicated. Okay, they're a bit complicated to calculate sometimes. So what we can do is, using this approach, we can find work done. Okay, so let me recap again. What's the process behind this? First, we want to check whether F is conservative. Okay, force fields don't have to be conservative. Some force fields are non-conservative. Some force fields are conservative. Okay, so we want to check first whether it is conservative or not. And how do you do that? First, you do nabla cross F. Okay, if it turns out that nabla cross F is the zero vector, then it is conservative. Okay, and what is the special property behind conservative forces? Is that the force field has a potential function. Okay, potential function, which we call phi. Okay, and what is the potential function? It is a function such that when you take nabla of phi, it will give you back the force field. Okay, using this, right, we can solve for phi. Okay, solve for phi. Okay, so phi is our unknown here. Okay, this is our unknown. Okay, we solve for phi, and then after that, to find the work done from point 1 to point 2, okay, to find the work done from point 1 to point 2 of this conservative force, what we can do is simply take phi 2 minus phi 1. Okay, so suppose the coordinate of this is 1, 2, and then suppose the coordinates of this is 7, 3. Okay, just as an example. So once I found the potential function, right, instead of doing the line integral, which could be complicated, what I can do instead is calculate phi 2 minus phi 1. Okay, in this case, it is phi at the coordinate 7, 3 minus phi at the coordinate 1, 2. Okay, then this will give you the work done, which is going to be much simpler. Okay? It's going to be much simpler than doing a line integral. Okay, so yeah, we can hop into this question and see what I'm talking about. So let's check whether this force field is conservative. So to do that, remember, we need to check the value of nabla cross F. Okay, so remember the definition of nabla. It is a column vector filled with partial derivatives in each component. Okay, so nabla is partial x, partial y, partial z. Okay, so remember, I'm just abbreviating the partial derivatives. Technically, you should write it like this, but it's too much to write, so I'll just abbreviate it like this. Okay, then the force field that they give in the question is given by So I'm writing this in column vector format. So there's no z component, right? How do I know there's no z component? Because there's no k, right? If there's a z component, it should have something with a unit vector k. But then this doesn't show up, so that means the z component is 0. So that's why I'll just fill in this entry with 0. Okay? And then remember how to do cross product of two vectors? What you need to do is find the determinant of this structure. And the structure that I'm talking about is first, in the first row, you put the unit vectors, ijk. In the second row, you put the entries of the first vector, namely nabla. Then in the third row, what you put is the entries of the second vector, which is this one. Okay, so to find the determinant of the structure, what we need to do is the crisscross method. So what you do is copy, paste, okay? So attach the first two columns on this side, okay? So you copy the first two columns, put it on the right-hand side. Then what you do now is find the crisses. So this time, this, and this. So on each line, we multiply all the entries together, okay? So this means I'm taking partial derivative of 0 with respect to y, okay? Which is just 0, okay? So fortunately, the result of the first cris is 0. Then what about this one? This one says I'm taking the partial derivative of this expression with respect to z. Okay, you see, partial differentiate this expression. Okay, so that's why I write this. But then remember, this is a partial derivative, so we treat any other variables as constants. Here we are differentiating with respect to z, so x and y are constants. All of these are constants. So differentiation of constant is 0. Okay, so just nice. The second cris is also 0. Let's take a look at the last one. So the last one says partial differentiate this expression. Okay, so let us go ahead and do that. Okay, so this is with respect to x. That means y is a constant. Differentiation of a constant is 0. Then this one is power bring down, power minus 1. Okay, so the third one has an entry. So you see, what does the last cris say? It says partial differentiate this expression, then multiply it by the unit vector k. Okay, so don't forget to multiply by the unit vector k. So 2x k. Okay, now we need to do the crosses. Okay, so now cross. So cross, cross, cross. Okay, notice the first one says partial differentiate 0. So that means this one is 0. Then the next one says partial differentiate that expression with respect to z. But the thing is, this expression contains no z terms. So it is treated as a constant. So differentiation of constant is 0. Okay, and then let's move on to the next one. The last one says partial differentiate this expression with respect to y. Okay, so let's do that. Partial differentiation of this expression with respect to y. So that means x is seen as a constant, so you can treat this as a constant. So you just leave it untouched. And then we differentiate this with respect to y. Okay, so -1 is just a constant, and then y, differentiation of y is just 1. So I don't need to do anything. Okay, so don't forget you need to subtract this expression away. And also you need to multiply with the unit vector k, right? See, it's this differentiating with this, and then don't forget to multiply with the unit vector k. So subtract, and that 2x and the k. You see, notice that 2xk minus 2xk will give me 0, okay, which is the 0 vector. Okay, this is actually the 0 vector. Okay, so you see, so let me summarize what we did. We tried to find the curl of f, right? And it turns out that the curl of f is 0. Okay, so since the curl of f is shown to be 0, that means we can say that f is conservative. Okay, so this is how you check whether the force field is conservative or not. You must check whether nabla cross F is equal to 0. Okay, having shown that it is conservative, right, then you know that it must have a potential function. Okay, just a reminder, only conservative forces have potential functions. Non-conservative forces do not have potential functions. Okay, so that's why you must always check whether a force field is conservative or not, because only the conservative ones have potential function. Non-conservative ones do not have potential functions. So the non-conservative ones, in order to find work done, you must use line integrals. Okay, so let's continue. So yeah, now our next step is to find a potential function. And then remember, the definition of potential function is a function such that nabla of f is equal to the force field. So let's write that down. Okay, so remember, the definition of nabla is just this. Then phi, we just treat it as a scalar number. Okay, just like any ordinary numbers. Okay, f is the force field that we have just now. Okay, so this one, 2x, y, this. Okay, so I obtained this from the question. Okay, so what do we do with the left-hand side? So remember, we treat this like a number, right? And then when we take a number multiplied by a vector, we just multiply that number into each entry, to the x entry, to the y entry, to the z entry. So we'll just do that. Okay, but in this case, it's not exactly a multiplication. What you're doing is differentiation. You're letting the x entry operate on the phi, the y entry operate on the phi, the z entry operate on the phi. Okay, so remember, this is partial derivative. So partial derivative is phi x, phi y, phi z. Okay, and just again as a recap, this is my notation for partial differentiation, because phi x is equal to d phi dx. Okay, but I don't want to write d phi dx because it's too much to write. So yeah, you equate it with this right hand side that you got just now. Okay, so because the z entry is 0, we don't need to care about this. We only need to care about the two entries. So equate the corresponding entries. That means the x component, you equate it with this. The y component, you equate it with this. So let's go ahead and equate the x components first. So from the x component, we found that phi x is equal to 2x y minus 1. Yeah, 2x minus 1. Okay, so this equated with this. Okay, so don't forget that phi x, right, is my abbreviation for partial phi, partial x. So in order to make phi alone, we need to integrate both sides, because integration is the opposite of differentiation. Okay, so integral can cancel the derivative, leaving behind phi. Then you're integrating with respect to x, so everything else can be treated as a constant. So x, you need to power plus 1 divided by new power. Then y minus 1 is just a constant. Then don't forget, you need to plus c of y. Okay, so don't forget, when you're doing partial integral, your arbitrary constant is a function of the other variable. In this case here, the other variable is y. Okay, 2 and 2 can cancel, leaving behind this. So I'm gonna expand this out. Okay, now we have to equate the y components. So I'm equating this with this. Okay, so to make phi the subject, we need to integrate both sides with respect to y. Integral can cancel with derivative, leaving behind phi. Then this is just a constant, so just plug in a y, and then this one you need to power plus 1 divided by a new power, plus, don't forget the arbitrary constant, which is now a function of x. Okay, so remember, if you integrate with respect to y, arbitrary constant is a function of x. Okay, cancel, cancel. Okay, so now we have two results for phi. This result, and then this result. So what I want to do is compare these two results to find the arbitrary constant. Okay, so let me just copy this first so that you can easily compare. Okay, so let's take a look at these two versions of phi. Okay, so focus on this result. So let's play this matching game. This term matches with this term, right? Okay, then now the only difference is between the two lines is this, right? Because the first two terms match. Okay, so this is telling me that this c of y is actually y squared. This c of x is actually minus x squared, because c of x means it is a function of x. You see, x squared is a function of x. C of y means it is a function of y. Y squared is a function of y. Okay, so that means by comparison, cx is equal to minus x squared, and cy is equal to y squared. Okay, so I'm just gonna plug in, for example, I'm gonna plug in, what did I do? Okay, I plug in this one into here. Okay, it doesn't matter if you plug in this into here, you'll get the same thing. So phi is equal to x squared minus x, sorry. Okay, so like I said in earlier tutorials, you actually need to put a plus k here. Okay, but okay, I'll just continue to say what I say when we do the next question. Okay, so the next sub question is find the work done. Okay, so the work done starts from this coordinate to this coordinate. Okay, starts from 2, 0, and it ends at 1, 1. Okay, so remember, once you know that this is a conservative force, it is very easy to calculate the work done. The work done will simply be phi 2 minus phi 1. So the value of phi at the end point minus the value of phi at the start point. So phi 2, remember, it ends at the coordinate 1, 1. And then phi 1 is 2, 0. Okay, so how do you find this value? What you do is you plug in, okay, what does this state? This states x equals to 1, and then y equals to 1. You plug in x equals to 1, y equals to 1 into this equation. Okay, you can ignore the k. Okay, when you find when you are finding work done, you can just omit the k. Okay, you just omit the k. So you plug in, x equals to 1, y equals to 1, x equals to 1, y equals to 1, then what you'll get is 1. Okay, now let's look at phi 1. Okay, so now this says x equals to 2 and y equals to 0. So what you do is you go back to your phi function. Okay, again, because for the purposes of work done, you can omit the k. Yeah, let x equals to 2, y equals to 0, x equals to 2, y equals to 0, and then you can calculate phi 1 will become negative 4. Okay, so if you do this, 1 minus negative 4 will become 5. Yeah, that's your work done. Okay, yeah, so this is the first question.